Hello, welcome to my channel. In today's video, we will learn how to introduce nonlinearity in activation function. Before jumping onto the question, let's first learn what neural network and activation function is. A neural network is a collection of algorithms that attempt to recognize underlying relationships in a set of data by emulating how the human brain functions. Neural networks adapt to changing input to produce the optimum outcome without refining output criteria. Neural networks take cues from the structure and operation of real brains in their creation. These models mimic the actions of neural networks of neurons by feeding features of interest via nested layers of perceptrons, each of which applies its own unique set of transformations to the data. Above is an illustration of a perceptron, the smallest unit in a neural network. In most cases, a perceptron will consist of three independent mathematical operations: scalar multiplication, a summation, and a transformation based on a separate equation known as an activation function. Since a perceptron represents a single neuron in the brain, we can put together many perceptrons to represent a brain. As such, activation function is a crucial part of any neural network. So, what is activation function? The output of a neuron is determined by its input using a mathematical function called the activation function in a neural network. The input is subjected to an activation function before generating the output. This function determines whether a neuron is triggered and transmitted to the next layer. It is known as the threshold or transformation for neurons because it determines whether or not the neuron's input is important to the prediction process. Activation function and nonlinearity. The primary job of an activation function in a neural network is to introduce nonlinearity. Without a nonlinear activation function, a neural network will behave identically to a single-layer perceptron, regardless of the number of layers it contains. At its most fundamental level, a neural network is made up of three primary layers, which are input layer, hidden layer, and output layer. Input layer is responsible for taking information coming into the network from the wider world. There is no computation done at this level. The only task is to forward the information that has been received on the hidden layer. The computations are carried out on hidden layer, and it is responsible for accepting information from the layer below it. This layer is not visible to anyone on the outside, and it is responsible for passing the result on the subsequent layer. The output layer is responsible for accepting the result from the hidden layer and then transmitting it to the rest of the world. The activation function is present in the hidden layer. The activation layer cannot be linear because regardless matter how complex the design is, a linear activation function is only effective one layer deep. This means that linear activation cannot be used. In addition, both the real world and the challenges that it presents are very non-linear. The only circumstance in which applying linearity could possibly be advantageous is when dealing with regression issues. Backpropagation is something that cannot be done with a linear activation function. As a result, utilizing it in a neural network is not something that is encouraged. Although it is possible for a model to carry out a job in a linear fashion, even when there is no activation function present, the model will suffer from a lack of accuracy and efficiency. The relevance of the activation function resides in the fact that it enables a particular model to learn and carry out challenging tasks. In addition, a nonlinear activation function makes it possible to form a deep neural network by stacking numerous layers of neurons. This type of network is required in order to learn large datasets with a high level of accuracy. Sigmoid function, 10H function, rectified linear unit, softmax function are some nonlinear activation functions. Now let's get to know some important details of these functions. Let's first talk about sigmoid functions. The range of the sigmoid function is 0 to 1 or -1 to 1. A sigmoid function is employed to translate a real value into a probability. The logistic function, also known as the logistic sigmoid function, is the most commonly used sigmoid function in machine learning and is typically referred to as the sigmoid function. Others are the hyperbolic tangent and the arctangent. The final layer of the model uses a sigmoid function to transform model's output into a probability score, which is simpler to use and understand. It can otherwise result in a neural network becoming stuck in the training phase, which is another reason to use it primarily on the output layer. Sigmoid is especially useful in binary classification. For example, if you are distinguishing between a cat and a dog by means of a computer vision algorithm, you want a clear answer that lies between 0 and 1, assuming that each number is associated with its respective animal. A 0 0.5 would mean that the algorithm was split between classifying an image as a cat or a dog, while 0.99 reflects higher confidence in a classification than a 0.8. Additionally, by squashing large positive and negative numbers, sigmoid saves neural networks from values that become exponentially larger as they are propagated through the network. Now let's get to know 10H function. The zero-centered function is another name for the hyperbolic tangent function, whose range is between -1 and 1. It is much simpler to model inputs with highly negative, positive, or neutral values since it is zero-centered. If the output is something other than 0 or 1, the 10H function is used in place of the sigmoid function. 10H functions are typically used in RNN for tasks like speech recognition and natural language processing. The function's gradient gets very small and gets closer to 0 for both sigmoid and 10H if the weighted sum input is extremely large or extremely small. We'll know about ReLU function, which is a shorter form of rectified linear unit. It is defined as f of x equal to max between 0 and x, where x is the input to the activation function. This means if the input is positive, the output will be the same as the input, and if the input is negative, the output will be 0. Rectified linear unit in neural networks is used because it allows for faster training and convergence, and it is less computationally expensive compared to other activation functions like 10H or sigmoid. It is less prone to vanishing gradients, a problem that occurs when the gradient of the activation function becomes very small, making it difficult for the network to learn. It is most commonly used in hidden layers of a neural network, and it is typically followed by another activation function in the output layer, depending on the specific task being performed by the network. Softmax function. It is used to build a multi-class classifier to solve the problem of assigning an instance to one class when the number of possible classes is larger than 2. Softmax ensures that sum of outputs is 1. The softmax function squeezes the outputs for each class between 0 and 1 and divides it by the sum of outputs. There are several ways to introduce nonlinearity into an activation function. Using a nonlinear function. Activation functions such as the sigmoid 10H and ReLU are all nonlinear. Using one of these functions as the activation function for your neural network will introduce nonlinearity into the model. Using multiple layers. Adding more layers to your neural network can also introduce nonlinearity, as each layer can learn to recognize more complex patterns in the data. Using a combination of linear and nonlinear functions. You can also use a combination of linear and nonlinear activation functions in your neural network. For example, you could use a linear activation function in the first layer and a nonlinear activation function in the second layer. Using a nonlinear activation function with a linear input. Even if the activation function itself is linear, if the input to the activation function is nonlinear, the overall function will be nonlinear. Using a nonlinear activation function with a linear input and a nonlinear transformation. Another way to introduce nonlinearity is to apply a nonlinear transformation to the input before passing it through a linear activation function. This can be done using techniques such as polynomial expansion or kernel tree. It is important to note that introducing nonlinearity is crucial for the neural network to learn and model complex relationships in the data. Without nonlinearity, a neural network would simply be a linear model and would not be able to learn more complex patterns. Here is the reference. That's all from me. Thank you.